And stoichiometry is basically just a fancy way of saying conversions for chemical reactions. Same way that we treat chemical reactions like algebra equations when in terms of balancing both sides, we can also write those as conversions because it allows us to talk about what we're using up or making in a specific ratio. And so we're able to solve a lot of word problems by using stoichiometry, which is, again, I don't know why they picked such an intimidating word for something that you guys should already be really good at. You just don't know it yet. I don't actually even know where the basis for where that word comes from.
It sounds Russian.
It's Russian, maybe Greek with the CH.
That's what you said. Why didn't you give us?
I'll check it. We'll talk about it on Thursday. So quick recap where we ended the other day. We had 5. This is the way we're going to break up our chemical reactions for this class. And again, there are lots of other ways of thinking about these, classifying these. It all depends on where you are, what class you're in. My OChem class has a totally different way of classifying reactions. It's very different than biochem, which is very different than chemical engineering. They're all going to have their own classification according to how they see things, what is important to calculate, what types of reactions matter to that particular field. At this level, since you guys are all going different directions from here, we're going to break it up into sort of the most fundamental level, which is things either change charges, electrons change hands, or they don't. Right? So these complexation reactions, we're changing the way things are arranged, but everything is still easily identifiable on both sides. Nothing is changing charges. No atoms are changing charges. If you have nitrate on one side, you still have a nitrate on the other side if it's a complexation reaction. Anytime you're changing the charge on an atom, it's this oxidation reduction classification. And all of these are sub-classifications of redox reactions. So all redox reactions just means charges changing hands, electrons changing hands. These are subcategories, right? So, and these first ones are, sometimes they take a little bit of practice to recognize, but they're pretty straightforward because, like I said, whatever you have on one side, you should also have on the other side. And it should be in the same form. So if it's an acid-base reaction, we're talking about moving a single H+. We're moving it away from one compound and sticking it on something else. So the only thing that should be changing if it's an acid-base reaction is the same formula on both sides, either just missing an H+ or with an extra H+ compared to where it started. All right, so for instance, these two polyatomic ions that you all nailed on the quiz, right? Sulfate, hydrogen carbonate, or bicarbonate. If they react, and on the other side of the reaction, we just have hydrogen sulfate and carbonate, it's still carbonate, right? We just moved an H+. It's still sulfate, we just stuck an H+ on it.
Is the charge not -2 on CO3?
Thank you.
Thank you.
If it was -1, then we did have a redox reaction happening and something really weird was going on. So the fact that it's still carbonate in both cases, just with an extra H+ or missing an H+, tells us it's an acid-base reaction. All right, so these take a little bit of practice to look at, but now that you know your polyatomic ions really well, it should be pretty easy because a lot of them are going to be polyatomic ions. And the ones that aren't polyatomic ions are either going to be an acid or you're making something that's neutral, starting from something that's neutral. So for instance, NH3 plus H2O reacting to make NH4 plus and OH minus. Hydroxide is just water missing an H+. Ammonium is just ammonia with an extra H plus. So they started neutral. They weren't in polyatomic ion form originally, but the oxygen still didn't really change. It was the same oxygen in both cases. It's just missing an H plus. And that means overall, it looks like the entire molecule charge changed, because it did. But the oxygen itself started with the same number of electrons it ended with. And same with the ammonia going to ammonium, right? So you're looking to see, but that's really not any different. It's really the same thing with an extra H plus. So a lot of times, if it's what's called a neutralization reaction, you're taking things like an acid and a base and getting closer to being stable. A lot of times you'll have water as a product, and it'll either be starting as hydronium or hydroxide and turning into water, or you could start from hydroxide or hydronium, or you start from water and make hydroxide. Right? So the most common acid-base reactions are going to have water playing a role someplace because it's always around. A lot of times your charges on the entire molecule will differ by 1 because you're talking about moving a single H plus around. If you have an acid as a reactant and you don't have that same acid as a product, it must have lost an H plus, right? So that's another good clue that maybe we're talking about an acid-base reaction. But really, at its most fundamental, look for the same ion on both sides. Just one extra H plus, one fewer H plus. Precipitation reactions look a little different on paper, but again, you're still going to be able to recognize the same ions on both sides. So precipitation reactions are probably the easiest reaction type to recognize because they're very, very specific. You mix two aqueous solutions together and you make a solid ionic compound. Right, so, for instance, calcium chloride, aqueous. Calcium chloride dissolves in water. And let's say sodium carbonate. Also dissolves in water. When you mix them together, the calcium ions, so we'll take a second and talk about ionic compounds when they're aqueous. Really what we have in this case is the ions totally split up. Remember when they're in their solid form, we have those lattice structures that we talked about a little bit in lab, where you wind up with alternating positives and negatives. So if we had sodium chloride, we have sodium ions alternating with chloride ions. And they wind up alternating in all 3 dimensions pretty much indefinitely. When you dissolve them in water, they can't keep all these same lattice interactions, the same structure. It has to break them up. That's kind of what an ionic compound does when it's dissolving, is you're breaking apart these ions and basically surrounding them with water molecules instead. So when we have a reaction like this, what we really have, we don't really have calcium chloride. We really have calcium ions floating around and chloride ions floating around, and sodium ions floating around, and carbonate ions floating around. And if you mix them in a way where you put 2 ions together that don't dissolve in water, then they don't dissolve in water. They stick together and they make a solid crystal structure like that. Right? So in this case, calcium ions, when they bump into a carbonate ion, will stick together and not stay dissolved. So you wind up making calcium carbonate as a solid, and then the sodium and the chloride stay dissolved. To balance it, we would want to do that. So, like I said, these precipitation reactions always have the same format, which means they're pretty easy to recognize. You're mixing 2 solutions of ionic compounds together and you're making a solid. And there are there are tables basically where we could go through and say, okay, well, they're called solubility rules, and we'll spend more time with this next quarter. So here's a quick example, a solubility rule, a table of solubility rules. I thought that they had the table on here. Oh, it's not a table, it's just right here. Salts containing group 1 elements are soluble, period. Meaning column 1 will always be soluble. Basically, it's a list of rules that say this type of ion will always dissolve or will never dissolve. And so it's just a matter of seeing if we make certain combinations. That's sigma Aldrich, right? That's perfect. That'll work. It should anyway. So which ions are soluble? Well, all of the metals, all alkali metals, group 1, so sodium, potassium ions, are always soluble in water, no exceptions. Ammonium is always soluble, no exceptions. Nitrates, acetates, chlorates, and perchlorates are always soluble, no exceptions. Chlorides, chloride, bromide, iodide, are almost always soluble with some exceptions. So silver chloride, lead 2 bromide, mercury 2 chloride and bromide, those will form solids. So basically this is just a list of things. Okay, if I happen to make a combination that's insoluble, it's going to be a solid here. So in this case, if I didn't write out the product side for you, if you had a list similar to this, you can say, okay, well, I've got chlorides present. So I look on my list, chlorides right here. They're usually soluble, except for silver, lead 2, and mercury 2. I don't have any of those there, right? So my chlorides are not going to form a solid. Sodium is in this category. Soluble, no exceptions. So sodium is not going to make a solid no matter what. Calcium, I don't see on here necessarily, but which ions are insoluble? Well, sulfides, hydroxides, carbonates, oxalates, chromates, and phosphates are soluble with some exceptions. Or sorry, are insoluble, meaning that they'll form a solid. So carbonate will form a solid unless it's paired up with one of these. If it's paired up with column 1 or ammonium.
So this example, it's paired up with sodium, so it's soluble as aqueous.
So carbonate with sodium is soluble, so you can make a solution if it's sodium carbonate. But when you mix the two of them together, we pair up carbonate and calcium, which are insoluble, so they stick together to make a solid. So all a precipitation reaction is we happen to make some combination of ions that sticks together and doesn't stay dissolved. That's all that they are, which means nothing is ever changing charge. All of the same ions are present on both sides, right? So very clearly not a reaction where we're changing anything's charges. We're just changing what's attached to what, because this particular combination doesn't dissolve. Dylan?
Well, you said you're not changing charges, but when you're dealing with a hydrogen, isn't that exactly what you're doing?
We're changing charges on the whole molecule. I'll clarify that in just a second.
Okay.
You're correct. Sorry, I realize I've been drawing things off the top of the camera, so I should probably make this work better a little bit. That works. Okay. All right, so I'm not going to expect you to memorize these. This is the sort of thing where it'll either be given to you on the test, or I'm really more interested in can you recognize it than can you predict it at this point. All right, if I give you a reaction, I want you to be able to tell me what type of reaction it is. As you get better at this, you'll be able to do things like if I say, okay, this is a precipitation reaction, what is it going to make? That's when you would have to get a list of solubility rules and say, okay, what possible combinations do I have? Is there anything that's insoluble? Right, so we'll practice that in lab. But at this point, we don't need to worry about it. All right. Redox reactions is going to be our category of basically everything else. Anytime you can look at something and say that atom changed charges from one side to the other, it's going to be a redox reaction. All right, and the most obvious ones are when you just have metal ions. Or even if they're not written as purely as ions, where you can look at it and say, okay, well, I started with a metal and now I've got an ionic compound with that metal. So, for instance, if we had something like we did sodium metal plus water in lab today, right? And when that reacts, it makes hydrogen gas and hydroxide and sodium, or sorry, we'll put it as sodium hydroxide. And I realize this red is not the easiest to see, so I'll switch colors. Well, the second you can look at the sodium, say, well, it's sodium all by itself here, so what's the charge have to be?
Neutral.
It's got to be neutral, right? Because sodium on its own, and I didn't write a charge there, so the sodium has a charge of 0. The charge on over here is now it's +1, right? Because hydroxide's -1, so the sodium has to be a +1. As soon as you can recognize that the sodium changed charges, you know it's a redox reaction. Right? So redox is anything where you can say this atom, not this whole the whole molecule, because sometimes the molecule can change charge when you move an H+. Well, when you can point to a specific atom or element, say it's 0 here and it's +1 there. There. Then that means it's a redox reaction. Right? And so again, metals are the easiest to see it because with ionic compounds, it's either going to be neutral or have a very specific charge, right? Even if it's changing like lead 2 chloride reacting with water to make lead 4 hydroxide and HCl. You might not be able to tell exactly what's happening in all the different spots here, but at the very least, we can look at it and say, well, lead right there is a +2 charge, and lead there is a +4 charge. Therefore, it's a redox reaction, regardless of what else is happening, regardless of what other ways we have of classifying redox reactions. These are just some examples. There's lots of different redox reactions. The second you see a charge on an atom changing, boom, redox. That's at least half credit. If it's one of these more specific examples and you could get more specific on the test, good. But at the very least, be able to say, well, I don't know what it is, but it's definitely redox. Okay?
Sean, if you're giving us that formula on the test, we have to balance it out because there's more hydrogens on the right side than the left side.
So the way I write the test questions on the final,
Kind of like the live today, where it says to balance out.
even more explicit. So let me show you what we're looking at. So let's look at last year, exam 2. Where's my mouse? There it is. Basically, I give you a reaction, I very explicitly leave a blank for you to write a number for balancing. Then I say, what type of reaction is it? And then it says, find the moles of copper formed when we do this reaction. And that's when you do the stoichiometry step that we're going to learn today. They're all gonna be 3-part questions. Balance it, tell me what type it is, do some math with it. All right, so it'll be very obvious that I'm looking for you to both balance it and tell me what type of reaction it is. And in this case, based on what we just learned, we had copper. What's the copper charge on copper over here? +1. The oxygen's -2, right? So +1. And we're making copper metal, which is neutral. So what type of reaction is this? Redox. The second we can look at this and say the copper was +1 and now it's 0. Boom, redox. Right, and so this is actually what happens if you put copper oxide with iron metal. It'll react to make iron oxide and copper metal, because copper metal is more stable than iron metal. Iron is more reactive than copper. It's higher on the reactivity sequence that we were talking about in lab today.
So for this part of the test, you would just write the redox, you wouldn't write if it's a gas, combustion, or metal-metal?
So this would be metal-metal, right? Because both things that are oxidizing and being reduced are metals. So the most specific would be metal redox.
Got it.
All right, but does that answer your question a little bit as far as, how I'm going to structure this? Okay. Some redox reactions, if you happen to make something that is a gas, means that they start bubbling. So, and again, if you didn't have lab today, you'll see this tomorrow, but in lab, this was zinc with HCl, right? Actually, it was this exact reaction. Let me get back to where I can zoom in. HCl plus zinc turns to hydrogen gas and zinc chloride. Zinc was neutral, now it's +2. The hydrogen was +1, and now it's neutral. And we'll talk about with covalent compounds how we can tell what charges things are in just a second. But even without seeing that, at the very least, we see that the zinc's changing charge. Boom, automatically redox. In fact, that we're making a gas means we could put it in this gas evolution category. One of the reasons why I don't like the classification of reactions that the lab uses and some textbooks use is because you can have gas evolution reactions that are redox reactions, and you can have gas evolution reactions that are just acid-base reactions, where nothing is really changing charge. And so that's just because they both make a gas as a product doesn't mean that the reaction's really all that similar as far as what's actually happening. So I'm most interested in, can you tell me it's redox or not redox? Is the biggest differentiation. And then if you can further classify it from that, that's even better. And then the last one is also a very, very specific case. Combustion reactions. Combustion reactions are very specifically means something is reacting with oxygen. And in general, it means it's something carbon with carbons and hydrogens. So a hydrocarbon is reacting with oxygen, and it's always going to make the same products. The balancing will be different, depending on what the molecule is over here. But it's always something with carbons and hydrogens, and maybe something else, maybe more oxygens, reacting with oxygen to make CO2 and water. That one's harder to see why it's redox, and I'll show you how to figure that out. Because you can't these are all covalent compounds, right? It's not easy to point to anything in here and say where the charges are changing, right? When there's no ionic compounds, it gets a little bit trickier.
So it always produces carbon dioxide and water?
A combustion reaction will always produce carbon dioxide and water. And you can get a little bit more broad with this definition. Technically, when you burn any metal in oxygen and make an oxide, that can be considered a combustion reaction. Like the one we did in class, magnesium plus O2 goes to magnesium oxide. Some people would consider that to be a combustion as well, just because it's reacting with the oxygen and it looks like it's burning. But since that's less accurate, and in general, most of what we're going to consider are going to be hydrocarbons. If you happen to try to burn something that has something besides carbon, hydrogen, and oxygen, you get other weird products. One of the main components of smog in the 80s, in the early 80s especially, was if you burned gasoline in your engine that had sulfur or nitrogen in it, you made sulfur oxides and nitrogen oxides, which were really nasty and smelled bad and messed with visibility. So that would be a combustion reaction where you also had a plus SO3 as a side product, because you didn't start with something that was only carbon and hydrogen. You had carbon, hydrogen, and sulfur, for instance. So there can be other things in here, but the cleanest examples and the ones that I want you to recognize the most are going to be carbons and hydrogens, maybe some oxygens mixed in, and it's always going to make CO2 and water. Just in different ratios. Okay, so this is the combustion of methane, and it has this balancing where it's 1, 2, 1, 2. If you did the combustion of, say, propane is C3H8 plus O2, but it's still going to go to CO2 and water. We just have to balance it differently. Now it's going to be something like 3, 4, and I think this is a 5, if I'm remembering correctly. I'm not doing it that fast in my head. I'm just going from memory. 10 and 10, yeah. Right, so it's still making CO2 and water, and it's still oxygen reacting with a hydrocarbon, just in different ratios. That's why if you're really into cars, you actually have to change the tuning on your engines if you get a different fuel source. If you get fuel that's higher octane than normal, modern cars it's less of an issue because it's all computerized and it's handled automatically. But especially on old cars that had carburetors, you actually would have to go in, if you got better gas, you tuned your engine differently to get a different ratio of oxygen to your fuel source in order to make sure that you had get as much energy as possible out of that reaction.
Could we look at the reaction of ethanol in gasoline?
We can look at the reaction of ethanol. So ethanol is going to be C2H6O. It's still reacting with oxygen. It's still making CO2 and water. That means things are going to look a little bit weird now, because now we have two sources of oxygen on the left-hand side. So balancing this gets a little bit trickier. But if we just start by doing the carbons and then the hydrogens, we have a total of 7 oxygens on the right-hand side, and
Yes,
we have 1 here, so we need another 6. So having that oxygen as part of the molecule over here changes things. The reason it's a problem in cars, if you have ethanol, or especially in older engines, snowblowers, this is really relevant to us. Snowblowers, if you use gasoline with ethanol in them after a few years, you can never get all of the water out of ethanol when you're trying to dry it. It's called drying it, even though you're still left with a liquid. If you're trying to dry the ethanol, there's always going to be a little bit of water left over. And that little bit of water left over in small engines will wind up corroding the carburetor nozzles over time. So progressively, your engine, you can do everything right, but if you burn, in an older engine, if you burn gas that has ethanol in it, eventually you're going to have to rebuild the carburetor or replace it. In modern engines that have fuel injectors, that's less of an issue. So it's really, ethanol and gasoline is not an issue for most cars, but for things like dirt bikes, for things like snow blowers or lawn mowers, it can be a problem, and things don't last as long as they should. So us being on the state line, that means you can drive up to Reno and you can actually get gas from one of the Reno gas stations that has like 16 different choices for your gas. You can get ethanol-free gasoline, which would be the best thing to do. I just don't care about my snowblower enough to drive all the way to Reno every.
You could get it in Minden too.
Minden has some too, yeah. No, the one in Reno is the one I'm thinking of, because there's one in particular that's towards the airport that's got like, 7. I pulled up once. I'm like, I have to make this decision right now. There's that many choices of types of gasoline.
How efficient is this reaction compared to gasoline combusting in terms of energy produced.
It does okay. It's not as energy dense as gasoline. But it does all right. Basically, it's not as efficient as biodiesel, as diesel would be. Basically, the more carbons and hydrogens you have per oxygen, the better, because carbon-hydrogen bonds and carbon-carbon bonds have more energy than a carbon-oxygen bond. So the more oxygens you have, the worse in terms of a fuel source, in terms of energy density. The more carbons and hydrogens per oxygen, the better. So the problem is that ethanol is really, really cheap and easy to make, because you just take corn and you mash it and you ferment it, and then boom, ethanol, fuel additive. So it's really, really cheap to produce, and it's subsidized by the government because the government pays people to grow corn beyond what we actually have demand for. So there are much better fuel additives than ethanol, and ethanol will never completely replace gasoline because it just doesn't have the same energy density.
It always circles back to money.
It always circles back to money and supply. We have lots of ethanol in corn, so why wouldn't we try to make a fuel additive with it? And that makes our gasoline go further, even if it's not quite as good for the... and it is carbon neutral is the other aspect of it that's nice, is because the corn is making sugar by pulling CO2 out of the atmosphere. So when you burn the ethanol that you made from corn, you're not increasing the amount of CO2 in the atmosphere because it's carbon neutral. It was already started as CO2.
It's already been negated at that point.
Right. So that being carbon neutral is better than something that's sequestered underneath the surface of the earth for millions of years than burning that where you're actively increasing the CO2 in the atmosphere. So ethanol has its advantages. Biodiesel is better though. Biodiesel is basically taking the ethanol that you can make really, really cheap, and you can take corn oil that you also make really, really cheap because it's subsidized, or soy oil, soybean oil. And you can react them together to make diesel that you can just put in a regular diesel engine. And so biodiesel just means it's carbon neutral diesel. It's just hard to make sure that you remove as much oxygen as possible, or much water as possible from it.
So it has circled back to money because gasoline engines are only,
And inertia. It's hard to get people to change. Everybody already has cars. We're already used to getting a liquid fuel from a gas station. We're already set up to have semis that are designed to carry flammable liquid for thousands of miles to fill up these gas stations. So switching all that over to being electric, while better for the environment long term, takes time because nobody wants to spend extra money now on changing something, especially if it means you have to retrain your customer on how to buy it, right? Because retraining the customer to switch to something else is a big difference as well. Even if it's cheaper, even if it's better for them. Not believe the argument I had with my mom over buying an electric car. She said, well, it just won't work for me. So, well, there's charging stations everywhere. You just have to change how you get fuel, right? You plug it in and then you go get a cup of coffee and come back and it's done, as opposed to standing at the pump for 5 minutes. Still will take you the same amount. Anyway, sorry. I digress.
all of our problems have solutions. They're just not all profitable.
They're not all profitable. They're not all practical. But for the most part, yeah. All right. With these redox reactions, if it's not something where you can very clearly point to sodium is neutral and sodium has a +1, a lot of times we'll have to use what's called an oxidation state. And this page number might be outdated. We're on a different version of the textbook, so I'll double check that. And so when we have a redox reaction, the electrons have to come from and go somewhere. If I skip back for a second. When we had sodium at neutral turning to sodium +1, it lost an electron to do that, right? The electrons have to go somewhere. So we always have these things paired. It's oxidation reduction because you can't have one without the other. Right? Oxidation means specifically that you're losing electrons. And reduction means you're gaining electrons. It's another one of those times where, Ben Franklin had only guessed the other direction. It would have really changed the language here and made it make more sense. Reduction is gaining electrons.
It's losing charge.
Its charge is going down. Its charge is being reduced.
Can you say that again?
Yes, and I'll give you a way to remember it as well.
In reduction, it gains electrons.
Reduction is gaining electrons because your charge is being reduced. Reduction refers to the charge, not the number of objects. Right? So
It confuses us more that reducing agent is the other guy, right? I mean,
right. So let's talk about what oxidation and reduction are first, and then we'll bring in agents. So oil rig is the way I always remembered it. Or there's Leo the lion says grr. Lose electrons is oxidation. Gaining electrons is reduction. Or oxidation is loss, reduction is gain. Which again, when you put it like that without putting electrons in there anywhere, it makes it sound kind of like something from 1984. You know, war is peace. What is the three
War
lines?
is peace. I can't remember.
Yeah. Anyway, yeah. There's
Good
the
purposes. I read that book.
is a good one. It's very, very big brother to say reduction is gain. But in this case, it's because we're talking about charge. The charge is being reduced. So that means it's gaining electrons.
Electron oil rig.
Electron oil rig. Or this one works, losing electrons is oxidation, gaining electrons is reduction. Grr. Leo says grr. When we're talking about a specific reaction, though, a lot of times we will be referring to the reactants as either the oxidizing agent or the reducing agent. So before we get into that, though, let's go back and look at these. So, in this top example, sodium metal plus zinc ions turns to sodium ions and zinc metal. What's being oxidized?
The sodium.
So losing electrons is oxidation. Is the sodium losing electrons? Yeah.
Hell yeah, it is.
Yes. Oh, yes. It's positive.
It gets positive charge now, which means it lost an electron.
That's the reduction.
So that's an oxidation.
Wait, if sodium only lost one electron, how did zinc gain 2 electrons?
It's because this isn't totally balanced. So, and we'll talk about that in a second. Reaction is the sodium turning into sodium ion. The reduction is going from +2 to neutral. It had to gain 2 electrons to do that. So, and as Jordan pointed out a second ago, sodium loses 1 electron, zinc needs to gain 2 electrons. So in order for something to actually be balanced, the charge has to be balanced as well. So really,
Yeah.
we should have that there to make it a balanced reaction. Because now the number of electrons is balanced on both sides too. The whole thing on the left-hand side adds up to +2. The whole thing on the right-hand side adds up to +2. If this is not written as ions, if this is zinc nitrate turning into sodium nitrate, then the nitrates would take care of that, because when you balance the nitrates, you'll also balance the charge. All right, how about down here? If the zinc is going from neutral to +2, is that oxidized or reduced?
Reduced.
0
Reduced.
to +2,
Oxidized.
oxidized.
No, wait, yeah.
So, and here's
You don't have to try to make it feel very good.
here's the other way that I remember this, that keeps things straight, is that what do metals do when you leave them outside in the winter? They rust, they oxidize, right? Oxidation in popular language means rusting, right? Metals will oxidize. So if you're starting with a metal and it ends with a +2, it's oxidation. Right? If you're making a metal, that must be a reduction, because you had to start with a positive charge and end it's neutral. So it's the opposite of oxidation. Right? So it's another way to sort of make it make sense. If you're starting from a metal and now it's no longer a metal anymore, almost always an oxidation. Right, that's just one more way to try and remember it and make it make sense in your head. So what's being reduced?
Hydrogen? It's not really though.
What's the charge on the chlorine here? Let's treat this like it's an ionic compound. It's an acid, but let's treat it like an ionic compound.
Oh, it's neutral.
It's got to be, the whole thing is neutral, but what's the charge on the chlorine? Negative
One.
1.
Oh, sorry, I saw the 2 for hydrogen. not 1.
Hydrogen therefore has to be what?
Plus one.
Plus 1. What's the charge on chloride here?
Minus one.
Still minus 1, right? So did the chloride change?
No.
So the chloride was neither oxidized nor reduced. Nothing changed. Its charge is the same in both sides. The hydrogen went from plus 1. What's its charge here? 0. So there's your reduction.
Can we know that it changed charge because it left the chlorine? And there's 2 of them.
So the 2 doesn't come into play. The fact that chloride was a negative 1 because it needs to gain 1 electron to be stable on the periodic table, right? So the hydrogen has to be plus 1 to make it add up to a charge of 0. Right, so if I erase these, this whole thing was neutral. So if the chloride's negative 1, the hydrogen has to be plus 1. Here, we have 2 hydrogens and their total charge has to add up to 0. So each hydrogen has to be 0. We can't have any charge except for 0 on the hydrogens, right? So we went from plus 1 to a 0, which means our charge dropped.
Same diatomic have the neutral charge.
Diatomic elements, anything in its elemental state will be neutral, is neutral by definition, right? So metals, when they're neutral, that's its elemental state. Diatomic element, because you can't have, if you have H2, you can't have 1 hydrogen with a plus 1 and 1 hydrogen with a negative 1. They're covalently bound and they're both exactly the same electronegativity because they're the same element. So with that in mind, each hydrogen has to have a charge of 0 because they have to add up to 0. Here, where you have 2 different elements, one that's more electronegative than the other, you can have 2 different charges. All right, and that's our next thing we're going to do here. One more thing I want to clarify though is, so if the sodium is being oxidized, that means that whatever we put the sodium with has to be reduced, right? So the sodium is being oxidized, but we refer to it as the reducing agent.
The act of.
Because agent means the act of. Good, I like that way of phrasing it. The agent is it's doing something. So if it's reducing whatever you put it with, it must be being oxidized.
So what's oxidized is the reducing agent, what reduces the
Bingo. Oxidizing agent.
Yes, that.
Right, so it's basically just flipping your frame of reference. So sodium is being oxidized. If we flip our frame of reference and say, okay, therefore it must be reducing whatever I put it with. Right, so in terms of English language, it makes sense, but it's confusing. You have to keep them straight. Agent means we're flipping our frame of reference. Right? So agent, the word agent means we're flipping our frame of reference. If it's being oxidized, it's the reducing agent.
Being oxidized is happening to it, reducing
Is what it's doing.
It's what it's doing. Yeah.
Right. So it's in terms of money, it's like payer versus payee. You have the same amount of money changing hands, but whether you're being paid or paying someone else determines whether you're the payer or the payee, right? The paying agent is the one who's giving away the money.
Sodium has been paid, but it is paying.
So sodium is giving away its electron.
Right.
So it's paying, it's reducing whatever we put it with. So it's the reducing agent. right? And again, it's just a little bit of grammatical weirdness that happens with the English language. We just have to be careful when you see agent, that means we're talking about what is it doing to the things around it. All right, so let's talk about how do we tell if something is being oxidized or reduced if it's not an ionic compound. So in this case, I'm telling you it's a redox reaction, but that means we should be able to see the charges changing to some extent. If it's all covalent compounds, though, we have to get a little creative with how we look at their charge. And basically, it's going to come down to electronegativity. Right? We say that whatever's most electronegative in an element is going to have first dibs, essentially, at filling its valence. So in the case of water, so we'll write out water bigger over here. What's more electronegative? The oxygen. What does the oxygen want to be stable? And how many? 2. So basically, whatever the most electronegative element is, we just say, we're going to treat it like it's an ionic compound, even though it's not. And we're just going to say that this is going to have a -2 charge, because that's what oxygen wants to get. Whatever else is there with it has to be whatever it is in order to make the charge add up to the overall charge of the molecule. So water is neutral, right? So what does the charge have to be on each hydrogen? 1 plus. So it's a covalent compound, so it's not like the hydrogen actually has a +1. It's not like it's a separate ion, the way we think of ionic compounds. But for the purpose of determining whether something's oxidized or reducing, we're going to treat it like it's an ionic compound, basically. Excuse me. So how about in CO2? What's most electronegative gets to go first. So what's the charge on the oxygen?
-2.
Still -2, and now there's 2 of them, right? So what's the charge on the carbon?
4.
Or I shouldn't keep saying charge. It works the same way as dealing ionic compounds, but we call it oxidation state, because it's not like the carbon actually has a +4 charge.
It's theoretical.
It's a theoretical way of estimating how much access to electrons does the carbon have.
Why do you call it charge?
You can think of it like charge. It's not the wrong. It's for the purpose of this, it's not wrong to think of it that way. What's the oxidation state on the oxygen here?
Theoretical.
0.
Has to add up to 0, right? And it also has to be the same. So 0. So if the oxygen starts with a charge of 0, and on the product side, it has a charge of -2 or -2, was the oxygen oxidized or reduced? Reduced. So our reduction is actually going to be to both of these. Which means something had to change here. So the carbon ends as a +4. What is the carbon over here? Is carbon more electronegative than hydrogen or less? Hydrogen was our dividing line, right, between the metals and the nonmetals. Every nonmetal is more electronegative than hydrogen. So that means carbon gets first dibs on the electrons. So how many electrons does carbon need to gain to have a full valence?
4, right?
Carbon's right here, 1, 2, 3, 4. It needs to gain 4 electrons. So if carbon needs to gain 4 electrons, carbon's going to be -4 over here. And it goes to being +4.
So it lost 8 electrons.
So it needs to lose 8 electrons. Basically, it was in control of all the electrons over here. He was a big fish in a small pond because hydrogen is not very electronegative, right? All of a sudden you expose it to oxygen, and now oxygen's the big bully, and oxygen gets to be the one who's in charge. So carbon started with -4 and ends as a +4. Right? So combustion reactions, we can still look at them and say why they're a redox reaction. And looking at these charges, these oxidation states, that's always going to be your smoking gun. No pun intended. When it comes to determining whether something is a redox reaction or not. As soon as you can look at something and say the oxidation state changed, it's a redox reaction. Right?
Did
Go ahead.
it happen in hydrogen? I mean, didn't the charge kind of like theoretically change from the hydrogen?
Not for the hydrogen. The hydrogen started as +1 and it ended as +1. Hydrogen only has, the nice thing about hydrogen is tricky in some ways because it can be a positive or a negative, but then again, so can carbon. The nice thing about hydrogen is hydrogen can only have 3 different charges, right? It can be +1, it can be neutral, or it can be -1. But hydrogen can only ever have a total of 2 electrons. That means there's only 3 possibilities total for hydrogen. It's always going to be +1, 0, or -1. And when it's surrounded by all these nonmetals, every nonmetal is more electronegative than hydrogen. So when hydrogen's attached to a nonmetal, it's always +1. If hydrogen's attached to a metal, it's always -1. And when hydrogen is by itself, it's neutral. It's 0.
What is CH4?
Nothing. All right, so some textbooks have a slightly different way of presenting oxidation state. Sometimes they'll have they call it it's like a priority chart where they say, okay, whatever's highest on this list, you make this the right charge first. It's all electronegativity though. Fluorine is always going to be -1. Fluorine's the most electronegative thing there is, so fluorine gets first dibs always. If it's not fluorine, then it's oxygen. If it's not oxygen, you keep going down the list of electronegativities. Right, so I used to teach it this way. Now I just like looking at it in terms of oxidation or electronegativities. So I'm actually going to zoom in here so that you can't see that little chart. It still works for ions too. The oxidation state on an ion is just the charge, just like Jordan said, just like we've been saying. Oxidation state is basically a stand-in for charge for covalent things where we can't give every individual element a charge. So for sodium oxide, what's the oxidation state on sodium?
-1.
And there's 2 of them, right?
-2.
So -2. If you have an ionic compound where you've got a bunch of things together now, you might want to break it up. So as soon as you recognize that this is magnesium and carbonate,
Carbonate is -1. Going -2.
-2,
So is me.
So
magnesium has to be
yes.
+2. And even without knowing the charge on carbonate, we know the charge on magnesium because it's in the second column, right? So magnesium's got an oxidation state of 2+, and carbonate as a whole is going to have its own oxidation states. Now we can basically ignore magnesium and just treat these the same way we just did. So each oxygen has to be what?
-2.
-2. Oxygen's the most electronegative. It gets first dibs. There's 3 of them, and they're all -2. So what does the charge have to be on carbon?
6.
6+.
That's only if we're making it neutral. Carbonate's not neutral though, right?
Oh,
yeah.
4+.
4+, bingo.
Good question.
So it's just a reminder that if you have things you can break up into polyatomic ions, that actually makes this really easy, right? You have to pay more attention to it.
would we look at carbonate as its own agent, or would we look at carbon and oxygen as their own agents?
That's a good, we would refer to the, when we say oxidizing agent or reducing agent, we're going to be talking about the entire compound usually. And so you can actually have one compound that is both the oxidizing agent and the reducing agent if one part of it's oxidized and the other part's reduced.
Okay.
Which is a little confusing, so we'll get there and I'll talk about that again. Jen?
I'm a little lost.
Okay.
So what are we doing right now? Are we just trying to see like which of the elements is being oxidized?
So no, we're not even there yet.
Okay.
Because for something to be oxidized, we have to change
Right.
something, right? We're just practicing assigning oxidation state, period. And then to tell whether something's oxidized or reduced, we would look at the oxidation state, say, of magnesium before and after. So
We're going to use this in a minute.
exactly, this is practice. So if we have magnesium plus O2 forming magnesium oxide, the oxidation state on the magnesium here is 0, right? And it goes to being a +2. So oxidation and reduction is always going to be referring to a change. What we're doing here is just practicing how do we tell where it's starting or where it's ending. So both of these are in their elemental state, right? They're both neutral. So both of these are starting with an oxidation state of 0, oxygen and the magnesium. When they react together, we get magnesium with an oxidation state of +2 and oxide with an oxidation state of -2. So that's when we would come in and say, okay, well, the magnesium went from 0 to +2. Now we can say whether that's oxidized or reduced.
Oxidized.
In this case, oxidized. Which means
Reducing it.
it's the reducing agent because the other piece is what's being reduced. Here's our reduction.
And oxygen is the oxidizer.
Oxygen is the oxidizing agent. That's actually where the term oxidation comes from, is because originally oxygen is the most powerful and most common oxidizing agent that there is. So
But it's
before they
oxygen.
understood with electrons, where they just said, well, it's adding oxygen to this, so we're going to call it oxidizing.
So if you have, like, I cannot figure this out. If you just have like one element by itself and it's neutral, like.
Correct. Well, unless I specifically say it's charged. If I said, like, we're starting with Na+,
Sodium ion.
that's a sodium ion. So that's going to be, this whole thing has to add up to a charge of +1.
And then anytime you have more than one, it's gonna have the individual pieces of it.
The individual, exactly. Every time you have more than one thing, the individual pieces are going to have to add up to the overall charge of that molecule. Jen?
So what are we saying about sodium oxide? Like, what is it that we're saying?
Just that the sodium has an oxidation state of +1 and the oxygen has an oxidation state of -2. It's basically just like we're figuring out the charge, just like we were doing nomenclature. You're probably overthinking it because this is something that should seem really basic, right?
We're at the first step.
That's all we're saying.
Okay.
We're not trying to take it any further than that for now.
We're at the first step.
We're at the first step. So same thing for this one, calcium phosphide.
Diphosphide. No, wait.
No, it's ionic, so we
Yeah,
wouldn't.
that's ionic. That's ionic.
So calcium phosphide, calcium when it's an ion has to be what charge?
Plus,
+2.
that's right.
That's 6.
So the phosphorus has to be -3.
So for
Go
that
ahead.
is what you say, calcium 2 phosphate, phosphide?
We don't need to specify the charge because calcium's in our second column here, right? So it's always a +2. But good thinking. That is, most specifically, that's what those Roman numerals are. It's not actually supposed to be the charge, it's the oxidation state, technically. It's the same as charge for the most part.
Phosphorus, pentachloride.
So for phosphorus pentachloride,
Phosphorus is a +5, chloride is a +1.
each chlorine is one of our more electronegative elements, right? So we need to make sure the chloride satisfied first, which means the chloride each have to be a -1. And there are 5 of them. Which means our phosphorus has to be +5. Right, so this is where where it becomes clear it's not really charge, right? Because phosphorus it's a non-metal. It's never actually going to have a charge of +5. But when you put it with things that are more electronegative, it'll act like it's got a charge of +5.
So you can more easily see what is the reduction. What is the
Exactly.
oxidation.
Exactly. So the way we would actually use these, and this is where we're trying to go a second ago, if we said that we started with phosphorus pentachloride and the phosphorus turned into calcium phosphide, it's starting with a +5 and ending with a -3. So the charge dropped, right? That's a reduction. But that's where this all plays together, where it fits together with what we've been working on today, is that this is how we can look at where we're starting and where we're ending.
So is it safe to say then that the more electronegative element in a compound is always going to be the oxidizing agent?
Or reducing.
Let me think about that for a second. It's because it's better to think to know, okay, this whole compound or this part of this compound is going this direction. You kind of always have to come back to this because sometimes chloride can be attached to an oxidizing agent and sometimes it can be a reducing agent. It depends on what you're putting it with. And so it's kind of hard to make that judgment, that broad call. What it's always going to come down to is assign your oxidation states to both sides and see what's changing in which direction.
P +3.
Phosphorus has to be +3 because
CO
each
-1.
chloride is a -1. And there's 3 of them. Here's one nice thing about the fact that we spent so much time on electron configuration and talking about orbitals, is oxidation states, if it's a stable compound, oxidation states will almost always tie into, it's as though it lost the right number of electrons to have an empty valence. Phosphorus is a +5, that seems weird, but phosphorus is 5 elements away from the edge, right? So phosphorus is a non-metal. It won't actually lose those 5 electrons, but it can have an oxidation state that looks like it got all the way to giving away 5 electrons, making it the same electron configuration as neon. Phosphorus is a +3, would correspond to emptying its p orbital. Phosphorus is a -3, would correspond to it getting over to argon over here. Right, so it still ties back to orbitals. The stable oxidation states are usually going to be something that matches up with the orbitals. One more example of that real quick to make that point.
You have to go over CO2.
I was going to go with nitrate, nitrite. Nitrate, what's the oxidation state on nitrogen? Well, oxygen's more electronegative, so it's -2. So nitrogen has to be +5.
Just getting rid of all of its
That would be like it went all the way back to neon, or to helium, right? Again, you're never actually going to get that. It still has a full valence as far as counting electrons and doing Lewis dot structures. It's sharing them, but it's sharing them with oxygen in a way that the oxygen sort of has control over them, because the oxygen is more electronegative. Nitrite, so it's NO2 with a -1 charge. Each of the oxygens still -2, right?
+3. N would be +3.
So N would be +3. Would you look at that? looks a lot like it emptied its p orbital and got to having only filled orbitals. The other stable oxidation state of nitrogen would be if it gained all 3 electrons, which put it over at neon, so it'd be a -3. So every element is going to have a set of what these are the stable oxidation states, and most of them are going to correspond to emptying or filling. They're going to be as though it gained or lost enough electrons to get to full orbitals.
Does it nitrogen have a half to fill orbital?
Nitrate would be a +5.
Nitrite.
Nitrite would be it would be a +3. So it would be emptying the p orbital and still has the full s orbital. Again, it's not like it actually loses those electrons. It's just, it corresponds to, what's stable corresponds to matching up with the orbitals, because orbitals kind of control everything, which is why we spent so much time on them in the beginning. All right, we'll keep practicing with this on Thursday, and that's when we'll actually get to stoichiometry and doing more conversions in math.
Yay.
Yay.
And Sean, is anything due tonight or?
No. No. The IC is on 13th of the lab.
Yeah, so nothing due until Thursday.
And we're still going to have tomorrow, yeah?
You'll still have lab tomorrow. We're just gonna try and crank through and get the whole thing done in one day.
Cool.
Wait, but Sean, did you hear the news?
What's that?
At the Florida Institute of Technology, they grew tomatoes in Mars-like soil conditions.
Tomatoes.
Yeah.
That is cool.
Oh, and the Florida Institute of Technology.
Sorry?
They grew tomatoes in Mars-like soil. Yeah.
That is cool.
Oh, and the Florida Institute of Technology.
Sorry?
They grew tomatoes